details into these manageable internal weights and nodes. So what gets lost is often the statistical noise, the really low probability exceptions, the minor nonlinear dependencies.
For example?
In chemistry, a DI system might abstract some complex low-level quantum noise into a simplified parameter, just because that parameter is computationally cheaper to work with.
But losing that noise or those minor details, that leads to approximation error.
It is guaranteed to. Compression inevitably loses information. Loss of information leads directly to approximation error, and that is a direct source of hallucination risk. The system is operating on a simplified, compressed version of reality. So its outputs will occasionally and unavoidably diverge from the full chaotic complexity of the real world. We pay for speed with inherent approximation errors. It's a fundamental trade-off. Hashtag 3.4, inductive bias mismatch.
Okay, the final unavoidable category is maybe the most abstract. Inductive bias mismatch. Can you define that term simply for us?
Yeah, the inductive bias is basically the machine's simplified worldview. It's the set of assumptions that are baked into the model's structure. It's rules about patterns, linearity, continuity that let it learn efficiently from limited data.
So like a mental shortcut.
It's a shortcut. A common bias might be that a system assumes effects scale linearly with dosage. This bias helps it quickly make sense of new input.
But reality is often nonlinear. It operates under different rules in different domains.
Exactly. And no single inductive bias can perfectly match the full, often contradictory complexity of reality. And this is where the mismatch happens. So consider a DI system that's heavily trained on how molecules behave in liquid solvents at standard pressure.
Okay.
Its inductive bias is really strong in that domain. But then you ask it to predict the properties of a material undergoing plasma phase deposition, a high-energy, totally non-standard state.
The model's baked-in assumptions about reality, its bias, would just completely break down in that new environment.
Completely. The mismatch between the model's necessary simplified worldview and the actual complexity of the world can't be eliminated. It's a permanent feature of the design. When reality violates the model's bias, you get an inherent error space. So the inductive bias is essential for learning, but it also guarantees an irreducible level of necessary error. That's the final price of intelligence.
That's profound. Okay, so we've defined category A, the solvable errors of rigor, and category B, the necessary unavoidable errors that are actually the engine of discovery. This has to lead to a completely new architectural goal.
Yes, we have to accept that certain types of hallucination are just unavoidable. So we can't pursue this naive goal of zero hallucination. If we did that, we would have zero discovery.
So we have to change the focus from elimination to exposure. What is the guiding principle for a robust DI system, then?
The core design principle for discovery intelligence completely shifts the objective. The goal is not zero hallucination. The goal is zero undetected hallucination.
That is the essential takeaway. Hallucination is acceptable. It's even necessary when it is explicitly labeled as a hypothesis or an informed inference.
Right.
It's only dangerous when it's hidden and presented as unassailable fact. So the architect's job is to create systems that turn these hidden, corrupting errors into transparent, explicit hypotheses.
We shift the whole system from being a generator of certain answers to being a highly transparent mapper of knowledge boundaries. And the strongest tactic in this new framework, it loops all the way back to prevention.
We talked about the minimum condition set, the MCS, earlier as a specific mitigation. But here it's being elevated to like the core foundational strategy for reducing the entire possibility space for error.
Yes, forcing the user or an upstream system to specify all the required conditions before any inference is allowed is the single strongest, most reliable reduction strategy we have. And the sources are clear on why this works so powerfully.
Why is that?
Hallucinations require assumption.
If the input is underspecified, the model has to assume a context. It has to create a silent internal hallucination.
Right. But by enforcing mandatory conditions, the architecture removes the model's right to assume. And if the model has no room to assume, the space for hidden controllable hallucination just drastically shrinks.
So this constraint-driven approach, it forces rigor not just on the system, but on the user too.
Yes. It ensures the entire process starts from a foundation of verifiable precision. It's mirroring real scientific protocols where the experimental setup is half the result. Hashtag 4.2, multi-layer hallucination management.
So a robust DI system has to enforce this rigor at multiple points. It can't just be at the input. It needs these structured security checkpoints for knowledge integrity.
Layered defense. It's essential because errors can creep in at any stage. So we need a multi-layered approach to enforce that transparency.
Okay, walk us through the layers.
Layer 1 is the input constraint layer. This is the gatekeeper. Its entire job is validation, making sure all mandatory conditions, the MCS, are met and that the query is sound. And like we said, refusal to answer is a necessary and correct function here. If the input is ambiguous, the system shuts down the pipeline.
Okay, so refusal is the defense against ambiguity. Once the input is validated, where does it go?
It moves to layer 2, the evidence retrieval layer. This layer enforces that strict adherence to condition-matched data. This is where cross-context leakage is brutally filtered out. If you ask for the degradation rate in saline water, Layer 2 will physically block any data from freshwater trials from ever reaching the model.
It stops the system from building a confident answer on irrelevant data.
Precisely.
Yeah.
And then finally, after the model has processed that rigorously filtered evidence and done its inference, we hit the most critical checkpoint. Layer 3, the inference and output layer.
This sounds like the mandatory labeling layer.
That's exactly what it is. Its primary function is epistemic transparency, especially for that unavoidable uncertainty we talked about in Section 3. Every single output must be explicitly labeled and put into one of 3 buckets.
What are the buckets?
First, evidence-backed. This is fully supported, verifiable by the Layer 2 data with very low calculated uncertainty. Second, inferred. This is a controlled extrapolation, a necessary hallucination that goes beyond the data but is strongly supported by the model's generalizing abilities.
And the third?
Third is hypothetical. This is a high-risk, low-confidence prediction that's operating far from the training support, maybe even crossing an inductive bias boundary.
And regardless of which bucket the knowledge falls into, those tangible confidence and uncertainty scores we talked about, they have to be displayed.
Always. The system communicates not just the answer, but the quality, the stability, and the empirical boundaries of that answer.
So this entire architecture, it all leads to a behavioral shift, doesn't it? The DI system moves away from being a simple chatbot, which is designed to give a complete sounding answer.
And it moves towards being a transparent, scientific communication style. It's designed for epistemic completeness, accurately mapping the boundaries of both knowledge and ignorance.
It's a shift in the user's psychological contract with the machine. With a chatbot, you just want the feeling of a complete answer. But with the DI instrument, you need to be able to assess the risk of the answer.
Exactly. The system is no longer trying to hide its gaps or smooth over its assumptions. It's highlighting them as essential context for the data. And this requires a completely new, multifaceted response format.
What does that new mandatory format actually look like?
It has to communicate 3 distinct states of knowledge. First, here is what is supported by evidence. That's the verifiable fact base from Layer 2.
Okay.
Second, here is what is inferred and the probability of error. That's the necessary controlled hallucination, the extrapolation. And third, here's what is unknown, the constraint failure points. That's the boundary of the current knowledge base.
So with that structure, you're not just trusting the AI's final answer. You're assessing its claim boundaries and the rigor of the underlying evidence.
Yes. And that transformation, making the uncertainty and the assumptions explicit, it turns that necessary evil of hallucination into epistemic transparency. And that is the absolute sign of a trustworthy high-stakes knowledge system. Hashtag tag outro.
This has been a really rigorous deep dive. I think to synthesize our findings, the core truth from this research is that even with perfect data and amazing models, you can't eliminate hallucination.
You can't, because that probabilistic generalization is the very engine of discovery.
The DI systems accept this truth. But with the right constraint-driven system design, these potentially corrupting errors get transformed from hidden failures into explicit, labeled, and managed hypotheses.
And what does this incredibly rigorous framework mean for you, the knowledge seeker? Whether you're using these specialized DI systems or just relying on general models for important work, it means you should demand transparency, not just confidence, from any system you rely on.
Right.
If a system claims it's highly confident, but it can't point you to the precise condition-matched evidence, or if it doesn't force you to be precise with your own input, then the answer is already suspect. Your quality of output relies absolutely on the rigor of your input.
The lesson here is so clear. Intelligence comes with an unavoidable cost, the risk of necessary error. But the truly reliable system is the one that architecturally owns its uncertainty and highlights its own ignorance.
Which leaves us with a final thought, building directly on that role of controlled hallucination. If we accept that generalization and extrapolation are essential for true scientific discovery, and that these processes inherently involve making an informed guess into the unknown, What are the specific, non-negotiable architectural constraints we must universally place on systems that are explicitly designed to extrapolate past the boundaries of current observed fact? How do we safeguard the future of knowledge when the discovery engine is literally designed to be wrong some of the time?
Something to mull on until our next deep dive. Thanks for joining us.